Bismillahirrahmanirrahim. Hello, this is Amar. We are going with the chapter 2 of the Callister book, 8th edition. Second chapter is about the atomic structure and interatomic bonding. So basically, in previous classes, as we have seen that different materials are available, and that most of them are environment friendly. For example, metals, ceramics, polymers. So basically, in this chapter, we will look out actually what are the basic atomic arrangements and different atomic structures that decide what will be the corresponding chemical physical properties of that material. So in this lecture actually we will look into the different atomic bondings and the different states of energy they fill out within the electronic structure. So it is very important to understand the atomic structure before going for the further advanced topics. So we will in this lecture we will look into the basic atomic theories and models that were given about the position of electron. So we will look out for the unit atom. We will look out what will be its mass and what will be the mass for electrons, protons, neutrons, and what will be the arrangement of electrons, protons and neutrons within the single atom. And then further we will see how atoms combine with each other and share electrons with each other with different elements to form the ionic covalent, coordinate covalent bonds and metallic bonds, etc. And we will also see these are the primary bonds, and we will also look into the secondary bonds like van der Waals forces are hydrogen bonds. So secondary bonds are also called van der Waals forces or hydrogen bonds. So for example, we have seen in case of the for example, one of the arrangement of carbon within the diamond is tetrahedral. So tetrahedral arrangement of atoms within carbon make it very conductive, and not only this, it is about 4 times more conductive as compared to copper. So if we look inside the diamond structure and atomic arrangement of carbon, then the arrangement is in tetrahedral form. So, and we can check that they have the higher strength and very higher bond lengths are available. So and also they are very best conductors, and from the experimentation it is found that its conductivity is about 5 times higher as compared to copper. While similarly another form of the carbon is the existence of the graphite as well. But in case of graphite, what is the main difference between graphite and diamond structure, and what is the atomic arrangement that makes diamond more conductive and of higher strength as compared to graphite? In case of graphite, we will see that atoms are in larger chains but with weak forces. So we will see that in graphite carbon structure is arranged in such a way that they have the weak intermolecular forces. So different atomic arrangement within the graphite and diamond make them according to the structural arrangement of the atomic level. Similarly, we can see steel, as we have discussed in the previous class, that when we will cool up steel and when we will increase the cooling rate, and that is the basically processing property, then how the grain structure varies with respect to the cooling rate, and similarly what was its effect upon the hardness and strength of the material. So basically for all of them we need to understand the basic atomic structure and interatomic bonding. One thing is interatomic bonding that exists within the atoms, and other is the intermolecular bonding that exists within the molecules. So their importance is too much. This course is supervised by Mr. Zara Khan, assistant professor, and Muhammad Amar Akram, lecturer. So this is my brief introduction. You people have already seen. My major research areas are flow induced vibration and thermal management of the electronic components. Within the primary field, for example, primary field of the vibration, like condition monitoring, fault diagnosis, online condition monitoring, and for the secondary field of vibration, I look into the flow induced vibrations and static structural vibrations as well. In addition, I am also working on the renewable energy, how to improve the thermal management of the solar panels, and similarly we are also working for the different stages of the projects. So some of the industrial projects I have dealt with. If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. To understand this quotation, as you people are in the first year of mechanical engineering, you people need to go through the first 4 years. So after that you will understand the meaning of this quote. So some of my publications are also available online on Google Scholar. You can write down my name. Also one of the another publication that is accepted within the journal of annals of nuclear energy, and we have worked on the turbulence flow, and we have checked out what is the effect of the turbulence flow on the different geometric structures of the tube bundles that are used within the nuclear fuel rods, condensers, boilers, heat exchangers, etc. So this was the course objective of industrial materials. So we will look out into the different industrial materials, their development, and chemical properties of these materials, and also the structural behavior, as we have discussed in the previous class in detail. The basic OBs, you can see the course objective of this material science and engineering course is to introduce the students the concepts and the use of materials in the design and manufacturing field. So how to select different materials, and what is the importance of materials, and how we can study the atomic and molecular level properties of the materials. The students acquainted with the knowledge of material selection, study material behavior in different operating environment, and protection of material against the catastrophic failure. To have knowledge about the nature, types, and behavior of metals, ceramics, polymers, rubbers, composite materials, intelligent smart materials as well. So we will go through all of them in detail. To correlate activities of atomic molecular level of materials, chemical and physical behavior, including the mechanical, electrical, magnetic, optical properties, and what will be the effect of temperature upon crystals and phase change of different materials. To detect the cause of the material failures and adopt prevention techniques. To develop material for particular requirements by using thin film deposition techniques for achieving electronic, magnetic, and optical benefits. So it will be normally we study in the second session course. So I have already shared the recommended books by William J.R. Callister, and some other recommended books are also given below. For example, by Degarmo, Kosar, and Black. This is also very important book. Similarly, this is another book of Elements of Material Science and Engineering by Van. So, in lecture 1 basically I have introduced the lecture 1 with to introduce the fundamental concepts of material science and engineering. So, your lecture 1 was about fundamental concepts of material science and engineering. So, this was your lecture 1, and basically today we are going with lecture 2. This lecture is available online, that is lecture 1, and another lecture, that is the third lecture. Basically this lecture, it is your third lecture, it is also available online. Okay, and the continued recording is about the second lecture. Basically it is written that it is lecture 1. So, after that we will go smoothly. After going through the basics of atomic structure and correlation with mechanical, electrical, magnetic and optical properties, we will go for the solidification and mechanism of crystallization. That is basically your third chapter of Callister. And continuation of this chapter is also in this lecture, where we will check out the different atomic packing factors of the hexagon, closed packing structures, Miller indices, solidification of molten metals. So, this will be our next lecture, inshallah. APF of HCP, Miller indices, solidification of molten metals. So, till now we have gone through 4 weeks and 4 lectures. So, we have covered up our syllabus till here. 3 lectures will be uploaded, and this lecture will be recorded inshallah as soon as possible. And after this we will go for the more advanced material engineering course, in which we will go for the density computation through crystal structure, equilibrium diagrams and their industrial importance, interpretation of phase diagrams of ferrous and non-ferrous metals. This will be your basically lecture 5. And your lecture 6 will be about the deformation, recrystallization and grain growth with effects on material properties. This will be your lecture 6. Your lecture 7 will be about ceramic materials, their structure, mechanical properties and electromagnetic behavior. This will be your lecture 7. In lecture 8 we will go for the polymer materials and their structure. It may be possible we will combine these 2 lectures and we will make it lecture 7. In lecture 8 we will go with the physical and mechanical properties, thermoplastic and thermosetting polymers. In lecture 9 we will go with the industrial robots, environment effects on them and their restriction in use. In 10th lecture we will go with the composite materials and their characterization. In 11th lecture we will go with the formulation properties of composite materials. In 12th lecture we will go with the intelligent materials, magnetomaterials and smart structures. In 13th week lecture we will go with the behavior of materials in use, fatigue, corrosion, erosion effects and their control. In lecture 14 we will go with the material failure and the remedial actions. In lecture 15 we will go with the special topics, texture and coatings, what is the effect upon the properties, thin films and sputtering, photoelectric applications. And last lecture will be about special topics, and we will go with the NDT techniques of the materials and software package. We will check out what is the application of CES for the material selection, and we will also go with the class projects as well and most advanced materials that are nowadays involved for the prospects of the research as well. So, quizzes, we will be having 3 quizzes, 1 quiz from sessional 1 and 1 quiz from sessional 2, and final will be also, there will be a quiz from final exam as well. So, basically this is your 2 credit hour course, and we will have 3 quizzes. Each quiz will be of 5%. We will also have a 5% of assignment, and we will also go for the 15% sessional 1, 15% sessional 2, and 50% will be your final exam. It may be possible that we will combine 5% marks from the final and 5% marks from the assignment, and we will use them for the class project as well. Class project, material sciences and engineering. So basically our today lecture is lecture 2. Sorry, I have not updated this slide. So basically this is your lecture 2, and today we will go for the material atomic structure and correlation with the mechanical, electrical, magnetic and optical properties. So what material science we have seen, structure and properties relationship we have already explained, materials engineering, designing and predetermined properties. So we have seen what is the effect of the processing upon the properties. Processing have a great effect, for example, upon properties, and properties can change the structure of materials behavior as well. For example, this was your cooling rate, and we were discussing the hardness parameter, that was the property, how it varies with time of the cooling rate, and in response we were getting the different crystalline forms of the material. Some of them are the single crystal form, some are about polymers form as well, polycrystal forms as well. So within structure we will go for the subatomic level, atomic level, microscopic level and macroscopic level, and within properties we will go for the shape and size and mechanical, electrical, chemical, physical, optical and magnetic properties. So what is the how these properties are dependent upon the atomic structure, we will look in today lecture. So basically we people know that performance parameter of all the materials basically depends upon the pre-processing techniques, and pre-processing techniques will define what will be the structure behavior, and structure behavior basically depends upon how properties are interlinked with processing rate. So major components of material sciences are, for example, performance parameters and processing parameters. What are performance parameters? Depends upon properties. What are processing steps? Manufacturing of structure. For example, what was the total temperature material was heated up, and what was the cooling rate, and what were the environmental conditions, were there any addition of other materials, alloys composition, or we are just going for the pure metals, or if it is a pure metal, what will be the effect of adding the impurities within it, how the thermal conductivity, magnetic, electrical, physical, mechanical properties will be affected. So all of them depends upon. So the primary building block is the processing. This will define what will be the structure, and this will define the properties, and finally we can get the performance of material. So titanic issue I have already discussed in the previous class. That was basically on the 14th of April 1912. So North Atlantic Ocean, and because of the frozen temperature of the ice water, the ductile behavior of material was converted from its current behavior to the brittle structure, because brittle material behave and it results in the early deformation without any it result in the destruction of material without any permanent deformation. In case of the ductile materials, basically these kind of materials have ability to absorb energy, and they show early deformation before failure, while brittle materials absorb energy but they do not show early deformation and they show abrupt failure of the material. So that's why brittle materials are very dangerous, but again depends upon the application. So we have abrupt failure. So from temperature, we know that from 0 to 15 degrees C behavior was something else, and from minus 15 degrees C to 0 degrees C the behavior of material was brittle. So that's why the absorbed energy resulted in the in producing cracks, and these cracks resulted in the formation of holes, and finally the diffusion of water from the below surface. And within hours it was found that from 2 hours and 20 minutes the ship was almost unstable, and it resulted in the death of more than 1500 people as well. So these kind of disasters that are interlinked with the material failure. So we have seen the mechanical disaster was because of the steel failure. The grade of the steel used was behaving brittle behavior at a frozen point, and when get colder it was showing a brittle behavior. So that's why the abrupt failure of material was because of the higher energy spike, and there was a ship strike with the. Now we will look into the atomic structure and correlation with the atomic properties. We know that if we talk about a single atom, then it consists of electrons, protons and neutrons. Inside atom there exists a nucleus that is densely packed with the protons and neutrons, and electrons we can see that they basically exist in the form of electronic cloud surrounding the nucleus in different energy shells having different orbitals. Now it is very difficult to say that electron will revolve in a fixed shell. Basically the uncertainty principle, and that was about that the momentum and position of electron cannot be described at the same time. So before going for that, go through the short video. These videos are basically from YouTube, and different resources are used. You can also get access to these videos online.
Top 10 accidents in metal smelting.
Yes, we are going for the Bohr's atomic model.
Bohr's model of atom. Various models of the atom have been proposed by eminent scientists over the years. These models have increased our understanding of the atomic structure. Among these models, Rutherford suggested that electrons revolve around the nucleus in well-defined orbits, but there was a problem with this. The motion of electrons in Rutherford's model was unstable because any charged particle moving in a circular path emits electromagnetic radiation. Thus, the electrons would lose energy and fall into the nucleus, making the atom highly unstable. Then, which would be a better model of an atom? To overcome the objections against Rutherford's model of atom, Niels Bohr in 1913 proposed a new atom model. What does this model propose? It first proposes that electrons revolve around the nucleus in specific orbits, and these orbits are associated with definite energies and are called shells or energy levels. These orbits or shells are represented by the letters K, L, M, N. The maximum number of electrons that can be accommodated in a particular orbit is 2n to the power of 2, where n is the number of the orbit. Thus, K shell would have 2 electrons, L shell would have 8 electrons, M shell would have 18 electrons, and N shell would have 32 electrons, and so on. That said, what does this model next propose? It next proposes that the maximum number of electrons that can be accommodated in the outermost level is 8. And finally, it says that the orbit closest to the nucleus has minimum energy and the orbit farthest has the maximum energy. Well then, does an electron radiate energy by itself? Since electrons move in a particular orbit, they do not radiate energy by themselves. What happens instead is when an atom absorbs energy, the electrons get excited and jump into the next higher energy level. The electron can radiate energy and return to its original state or drop down to the next energy level. Bohr's model works well for simple atoms and is easy to understand. It is one among the atomic structures still in use today, and the other being the quantum mechanical model. Things to remember. In 1913, a Danish physicist, Niels Bohr, proposed an atomic model known as Bohr's atomic model. In an atom, the electrons revolve around the nucleus in definite energy levels called orbits or shells. The maximum number of electrons that can be accommodated in a particular orbit is 2n to the power of 2. The maximum number of electrons that can be accommodated in the outermost shell is 8. The orbit closest to the nucleus has minimum energy and the orbit farthest has maximum energy. Electrons are excited to the higher energy levels by absorbing energy and return to the lower energy levels by radiating energy.
Spectral lines of hydrogen atom. According to Bohr's third postulate, when an atom makes a transition from the higher energy state to a lower energy state, the energy is radiated in the form of a photon having certain frequency. The spectral lines arising from the transition of electrons of an atom from higher energy states to a definite energy state form a spectral series. The various spectral series of hydrogen atom can be represented with the help of orbital diagram of an atom, as shown in the animation. When a transition from higher orbits to the first orbit occurs in the atom, Lyman series is obtained. The values of frequencies obtained in this transition lie in the ultraviolet region of the electromagnetic spectrum. When a transition from higher orbits to the second orbit occurs in the atom, Balmer series is obtained. The values of frequencies obtained in this transition lie in the ultraviolet region of the electromagnetic spectrum. When a transition from higher orbits to the third orbit occurs in the atom, Paschen series is obtained. The values of frequencies obtained in this transition lie in the infrared region of the electromagnetic spectrum. When a transition from higher orbits to the fourth orbit occurs in the atom, Brackett series is obtained. When a transition from higher orbits to the fifth orbit occurs in the atom, Pfund series is obtained. The energy of emitted radiation is given by the formula shown here, and the Rydberg formula for the spectrum of hydrogen atom is given by the formula as given here.
So the same concept is also used for characterizing the unknown materials. We drop the waves of photon that are used to emit the radiations from the electrons. So whatever will be the atomic composition of that material, they will emit the corresponding energy of the particular wavelength, and it will be recorded, and with the available data it will be check out what is the corresponding electronegativity of the material and in which class this material is lying, and depending upon its wavelength and frequency we can characterize the composition of material as well. So Bohr's Lille model presented in 1913 was basically you can say the unit cell of the material science and engineering. So to explain the atomic structure was not easy task. You can see here protons and neutrons densely packed inside the nucleus. Protons carry positive charge and electrons revolving around nucleus in a specific orbits, forming the electronic cloud. So this is the charge on electrons, 1.6 into 10 raised to the power minus 19 coulomb, and this is the charge on protons, that is basically 1.6 into 10 raised to the power minus 19 coulomb, and neutrons chargeless, again we people know. And what is the atomic number? Atomic number is represented with the alphabet Z. It is very important to understand the atomic structure. Why? Because the bonding strength controls different material properties, and this material property, for example stiffness, physical, mechanical, electrical properties, will depend upon the bond strength, and this bond strength basically depends upon the atomic structure, behavior, and the type of bonds that are found within the atom, in between atoms and molecules. So we have equal number of protons and electrons in a neutral atom, and mass of electron is 9.1 into 10 raised to the power minus 31 kg, and mass of proton is nearly equal to the mass of neutron, and it is about 1.6 into 10 raised to the power minus 27 kg. And what is atomic mass? Atomic mass is nothing but it is the sum of mass of protons and neutrons. What is isotope? Same proton but different neutrons. Same proton but different neutrons. So sometimes we say that this is the isotope of carbon. So isotope means the atoms having the same protons but different neutrons, as explained previously. What is atomic weight? Atomic weight is basically the weighted average of atomic masses of the isotopes. It is also defined as the atomic mass unit of the unit of the carbon atom. So weighted average of atomic masses of isotopes is atomic weight. We can see here this is your carbon and atomic number is 6 and atomic weight is 12.011. So atomic mass unit 1 AMU means 1/12th of the isotope of carbon. Okay, so basically it means 1 AMU will equal to 1/12th of the atomic mass of carbon, and when we will solve it we will get this one. Avogadro's number is 6.02 into the 10 raised to the power 23 atoms per mole or molecules per mole. So we can see within nucleus we have proton and neutrons, and electrons are surrounding the nucleus. This was the Bohr atomic model. Electrons are assumed to revolve around the atom's nucleus in discrete orbitals. So we can see the electronic cloud. So probability of finding electrons was described by the quantum numbers. What was wave mechanical model? Wave mechanical model was the electron exhibits both wave-like or particle-like characteristics. So probability of finding electron will be different in case of the wave model and Bohr model. So we can see here the probability of finding electron for the wave model. So cloud represents the probability of finding electrons. So maximum probability of finding electron is here. You can see probability of finding electron here is maximum. And if we will go for the Bohr's model, then we can see that for a specific instant and time, the possibility of finding electron will be maximum, but it will be a maximum for just one instant and time. You can see here Bohr atomic model, electrons revolving in the orbits. So what are quantum numbers? Every electron in an atom is characterized by 4 quantum numbers. Shells are basically specified by the principal quantum numbers k, l, m and n shells. So this is your principal quantum number. You can see we have renamed k, l, m and n energy levels, and these shells are sometimes designed with this, and it illustrates the distance from the nucleus. Higher is the distance from the nucleus, higher is the energy level. You can say m is the higher energy level as compared to k shell. So one shell will be having one subshell, and 2 will be having 2 subshells, and third energy level will be having 3 subshells, and so on. Second quantum number signifies subshell. Basically, if we want to find the velocity of electron, I am giving you example, then what will happen? We will throw out the beam of photons upon the given material, and it will try to emit the electrons, and when electron will change its position, obviously it will also emit the radiation of a particular wavelength and frequency, but basically electron will scatter. So uncertainty exists, and we cannot say that atom can exist at a fixed place for all instants. So this is uncertain case, and we can guess that electron will be in this region with probability only. So wave-like properties of electrons give them discrete set of energy states. Okay, not continuous set of energy states. These are the discrete set of energy states: energy state 1, energy state 2, energy state 3, energy state 4. Discrete set of energy states. So discrete set of energy states, in order to understand different energy levels, electrons will first fill out the low energy level that are present near the nucleus, and then they will go for the higher energy levels. So first principal quantum number will be having one subshell, and maximum number of 2 electrons can be sustained in first subshell. number of electrons that can be sustained within the different principal shells depends upon the number of shell here. For example, if I am in M shell, then n will be 2. If I am in K shell, n will be 1. So K L. If I am in M shell, n will be 3. And another shell is first shell was K, second shell was L, third shell was M, and fourth shell was N. Similarly, if you are in the fourth subshell, for example N, so K, L, M, N, O, these are the principal quantum numbers and quantum energy shells where the possibility of electrons exist. And electron will come and fill this energy state first, and then the remaining electrons will be go there, and then remaining electron will go there, and finally left out will go here. So we can see first energy state has one subshell, second energy state has two subshells, third energy state have three subshells, this one and this one, and fourth energy state have four subshells, this one and this one. The number of energy states for each subshell is determined by the third quantum number. So when electrons will come and they will try to fill out 1s square first, and then it will fill out 2s square, and if there are remaining electrons are also there, then they will go for 2p6 3s square. In case of s orbital, we can assume that electrons are existing in the orbital having a spherical shape, and for s shape maximum number of 2 electrons will be there. For p shape maximum number of 6 electrons will be there. For d subshell we can have maximum number of 10 electrons, and for f shell we can have maximum number of 14 electrons. And how we can make these energy shells? Simply write down 1s square, 2s square, 3s square, 4s square till 7s square. Then from 2s square write 2p6, 3p6, 4p6, 5p6 till 7p6, and then start with 3 d10 and go down. Similarly, start with the 4f15 and go down. When you will draw the arrows pointing 1s square, 2s square, 2p6, 3s square, 3p6, 4s square. What is meant by 1s square? 1 means first energy level and s means s subshell. Similarly, 2s square means second energy level and s means spherical orbital. And what will be the shape of the p orbital? Basically, p orbital exists in 3 directions, x, y, z, and you can say if this is x, this is y, and this is z, then electrons may exist like this or this or this. So probability of finding electron in 3D space will be there. And fourth quantum number is the spin moment. If we talk about the spin moment, we can say that the maximum number of electrons that can exist within the one orbit are 2. Okay, so spin quantum number is represented by ms, and electrons not only orbit but they can also spin. Okay, and each orbit will have maximum number of 2 electrons. Each orbit will have maximum number of 2 electrons. So probability of spinning of electron, what does this mean? Basically, if it is the s orbital, then we can say that electron will revolve within the orbit, and also it will spin around its center as well. This is your ms, okay, and maximum number of 2 electrons can be there in one orbit. So probability of the clockwise and anti-clockwise spinning will be this, half. Similarly, we have a magnetic quantum number, that is ml, and it specifies orientation in space. ml is your magnetic quantum number. And another was the L, that was the angular momentum, and it give us the information about subshells. It also give us the information of the shape of the orbitals. Shape of orbitals. So this is basically your angular momentum quantum number. And K was the principal quantum number, that was describing energy states for different shells. So you can see here maximum 2 electrons in one subshell, but with opposite rotation. So spinning motion will be either clockwise or anti-clockwise, and probability is half for each. So you can see here the principal quantum number 1, 2, 3, 4, and shell designation KLMN, and subshell for first principal quantum number will be S, for second quantum number will be S and P, for third quantum number will be S, P and D, and for fourth quantum number will be S, P, D and F. Maximum number of electrons, this is the number of state, that is with respect to the filling of electrons. First electron will go there, then it will go there, then it will go there, and so on. Number of electrons per subshell, you can say S can accommodate maximum number of 2 electrons, P can accommodate maximum number of 6 electrons, D can accommodate maximum number of 10 electrons, and F can accommodate maximum number of 14 electrons. Okay. And if we will talk per shell maximum number of electrons, it will be given by formula 2n square. So if it is the first subshell, if it is first shell, we will have 2 answer. If it is second, put here 2, and 2 is equal to 4 into 2, 8. And if it is third per shell, then 2n square, that is equal to 2 into 3 square, and it will be 18. And similarly 2n square, that will equal 2 into 4 square, it will be 32. So what are the valence electrons? Electrons in the outermost shell, if the outermost shell of the atom is completely filled with electrons, then its behavior will be stable. Stable atoms normally are not interested for any relation and any chemical reaction. So they are not interested for making any chemical bond, because they are stable and they have a complete valence shells. But sometimes the valence shell will have spaces left out, free spaces left out for electrons. You can say that energy state, outermost energy state will be not completely filled, or it will be unfilled. So this state of the shell will make it, because of the electronegative difference, it will go for making a chemical bond with other atoms. So electrons in the outermost shell, maximum number of 8 electrons, determine physical and chemical properties. So here you can see this is your periodic table. In case of periodic table, we have a total number of 118 elements, and you can see that we have vertical groups and horizontal rows. Horizontal rows are also called periods. So we have total number of 7 periods: 1p, 2p, 3p, 4p, 5p, 6p and 7p. Okay. So what information we can get from periods? They will give us information about energy state or energy shell. For example, if I am working on lithium, because it is present in the second period, so you can say there will be 2 energy levels or 2 shells, K and L, in case of lithium. Similarly, in case of potassium, we will have 4 energy levels and so on. So this is information about periods. And vertical columns are called groups. In periodic table we have 18 groups, and also we can see, we can get information about valence electrons from groups. So basically groups can tell us about valence electrons. For example, if I am in 7a group, then I can say the valence electron in the outermost shell will be 7, and if it is here, you can see this is your basically inert group. It have outermost shell filled up, maximum number of 8 electrons. So that's why if it is first subshell, the maximum number of electrons will be 2, and if it is second subshell, maximum number of electron will be in outermost shell will be 8 and so on. So we can say that inert gases have the complete outermost shells, they have no valence electrons, and in this way they are non-reactive, they are not interested for the chemical bonds. So basically when we talk about periods, periods have the same chemical properties. Why? Sorry, not period, groups, I am talking about groups, columns. Okay. So basically groups have the same chemical properties. For example, if this is your inert gas group, then they will all will have same chemical properties. Okay. Group 1 is your group of alkali metals, and you can see here the valence electrons will be 1 or outermost electron will be 1. So that means alkali metals are highly reactive and they can make bond with the other atoms. Okay. Your 17th group is the halogen. This is your 17th group. This is your basically halogen group. And in case of halogen group, you will have a 7 valence electrons. I am writing here halogen group will have 7 valence electrons. So noble gases are highly unreactive and they can prevent a chemical reaction. For example, you have heard about argon. Argon is filled up in light bulbs to prevent oxidation of filaments because they are chemically inert. Okay. In addition, when we talk about atomic radius, then we can say atomic radius will increase from right to left. Why? Because the number of valence electrons will increase when we will go from right to left, and when valence number of electrons will increase because there are more electrons in the outermost shell, and the atom will be packed up and radius will decrease. And similarly we can see from top to bottom, sorry, this will be radius will yes, here you can see the valence number of electrons will be more, so that's why here we have small radius, and when we will go from the right to left, and then what will happen, radius will increase. Similarly, when we will go from bottom to top, then radius will increase. Again you can see because number of valence electrons will decrease when we will go from bottom to top, and because of decrease of the number of electrons in the valence shell, so what will happen, because of decrease of the number of electrons, that electrostatic forces will decrease and atomic radius will increase. Similarly, this is the concept of atomic radius. And if we will talk about the ionization energy, what is ionization energy? It is the amount of energy that is required to remove electrons from an atom. Okay, it is the amount of energy that is required to remove electrons from an atom, and it increases from bottom to top. Why? Because here we will have smaller radius and here we will have bigger radius of atom for higher electrons. Okay, because from bottom to top radius will increase, and because of increase in radius, the nucleus force of attraction will also decrease for the electrons. So that's why we will need small amount of energy to remove the valence electrons. So ionization energy also increase from bottom to top. If we will talk about the electronegativity, it is the tendency of atoms to attract electron towards itself. Electronegativity, it is tendency of an atom tendency to attract electron pair. So its behavior will also be like ionization energy, and we will see when we will go from bottom to top, or when we will go from left to right ionization energy and electronegativity will increase. Because here we can see with increase in the number of electrons, if we will go from the left to right, for example neon, if we will go from left to right, then we can see we have more number of electrons in the shells. So that's why we will need higher ionization energy, or electronegativity value will also be higher. And in this case you can see only 3 electrons are in lithium. So in case of neon we have 10 electrons. So in case of lithium we only have 3 electrons. So in case of lithium we need a small ionization energy to remove electrons, and for neon we need large or higher ionization energy to remove electron. Similar is the case for electronegativity. So electronegativity is the measure of the tendency of atom to attract a bonding pair of electrons. Electronegativity increase in moving from left to right and bottom to top. Okay. You can see the minimum value of electronegativity is 0.7 and maximum value of electronegativity is, for fluorine you can see 4. So fluorine is highly electronegative element and F4 is the lowest electronegative element. So for the red color mentioned here in periodic table represent electronegativity. So after going through this, now we have the basic knowledge of periodic table and the Bose atomic model. Now we can go for the chemical bonding as well. Now we will check out what are the different kinds of chemical bonds that exist. For example, metallic bond, ionic bond, covalent bond, coordinate covalent bond. They are all primary bonds, and most of the material go for the primary bonds, although they also have a secondary bonds like van der Waals forces and hydrogen bonding as well. Ionic bond is because of difference in electronegativity values, and this difference will be very larger. So ionic bond is always because of the higher electronegativity difference, and ionic bond is also non-directional. Covalent bond is directional. We will see example as well. One atom will give its electron and it will be valence electron, okay, and another one that will be non-metallic will accept that electron. So one atom will lose electron and other will accept electron. So here you can see sodium will become sodium ion and chlorine will become chlorine ion. Sodium have lose one electron, so it is Na plus, and chlorine have accepted electron, it is Cl negative, and there will be a existence of the higher electronegativity, and it will favor for the ionic chemical bond. So chemical bond in between them will be ionic and it will be non-directional. Sodium is the metal and you can see chlorine is non-metal. So you can see this equation as well. So Na and Cl join to form NaCl. So ionic bonds characteristically hard, brittle, electrical and thermal insulator materials. So materials which will form ionic bond will be hard, they will be brittle, and also electrically and thermally they insulator, material will be thermally insulator. So greater distance between like atoms, bond strength depends upon ionic vacancies or valences. So here we can see the ionic coordination number, central atom surrounded by the for example cation is surrounded by the anion, and we can see here we have the 4 coordination number 1, 2, 3 and 4, and center atom here is again coordination number is 4, and in this case we can see central atom is surrounded by 3 atoms, so coordination number will be 3. Maximum coordination number is dictated by the ratio of the radii, small r divided by capital R, where r is the radius of the smaller ion, almost always positive, and r is the radius of large ion. So you can see this is smaller radii and this is larger radii. And let's find the coordination number. Example is that in an ionic compound XY, the ionic radii of X plus, that is positive ion, and this is your negative ion, they are 150 pm and 189 pm picometer respectively. Calculate the coordination number. We will use the formula of radius ratio. For example, ratio of the smaller radius for positive element and larger radius for the negative element. So these are the radius, and when we will get the ratio, it will be 0.794. Now we have to look this ratio within the table. This table will be given and we will check out where it is lying. So we can see 0.794 lies in this row between 0.7 and 1. So that means possible coordination number is 8 and its structural arrangement will be cubic. Example is CSCl. Another very important and very strong bond is covalent bond. It is directional dependent. So a directional bonding between atoms, so there will be sharing of electrons between adjacent atoms take place. So there will be sharing of electrons in case of covalent bond. Smaller difference in electronegativity favors covalent bond. So if there is larger electronegativity difference, it will prefer ionic bond. Okay. So look here the example. Hydrogen having one valence electron and maximum number of 2 electrons can be there in valence shell. So two hydrogen atoms are sharing electrons with each other, and in this way we are getting the H2 molecule that is now chemically inert. It have filled up valence electron and it will lie in the inert gas group. This is another example, tetrahedral structure of the diamond. Carbons are arranged in the tetrahedral form in case of diamond, and that's why diamond have higher K conductivity value, higher value of the melting point as well, and other thermal physical properties will also be higher. Okay, while in case of graphite, layers of the carbon basically they will lie from end to end and in such a way that they will exist with the weak binding forces. For example, you can see the layer of atoms, although they have carbon-carbon bond. Okay, carbon-carbon bond exists in graphite as well, and carbon-carbon bond exists in diamond as well. But what is the main difference? That carbon-carbon atom in graphite will make layer structure, and in this case of diamond it will make tetrahedral structural. In addition, the attraction between layers will result in the formation of weak binding forces. Weak binding forces, and it exists in case of the graphite only, while in case of diamond there will be a very strong ionic bond So that's why diamond structure have very high value of the thermal conductivity, and similarly it will have the very higher strength as well. Melting point will be higher, boiling point will also be higher, and it can also store the amount of energy for a large time as well. While in case of graphite, you can see a difference. So basically, because of the presence of these weak binding forces, graphite is weaker, have a weak structure as compared to diamond, and thus graphite have a low thermal conductivity and low melting points and strength as well. So in case of the diamond, carbon has a coordination number of 4. Okay, very important thing. In case of diamond, coordination number is 4. So that means it can make a tetrahedral structure, and it will make 4 atoms bond. So it will make a bond with the 4 surrounding atoms. While in case of the also diamond is also a very strong carbon, and it is covalently bonded with the 4 other atoms. So there is a covalent bond that exists between carbon atoms, but there is existence of only covalent bond. Okay, and it have a tetrahedral structure as well. While in case of the graphite structure, in addition to covalent bond that exists in between carbon-carbon bonding element, but there is also a existence of the weak binding forces in between layers. So because of the weak binding forces in between layers, graphite is have a coordination number of 3. You can see here. So graphite has a coordination number of 3, and these graphite layers will be bonded to each other with the weak binding forces. So that's why it have a low thermal conductivity and low covalent melting point, boiling point as well. So this is your coordinate covalent bond. In case of coordinate covalent bond, you will see that there will be a complete lone pair donation. For example, in this case you can see one extra pair in case of the nitrogen that is available, and one extra pair is required by the boron as well. So what will happen? This lone pair will be completely donated with boron. So one atom is called donor, and it is also known as ligand. So in this case, nitrogen is your ligand, and it will form a coordinate covalent bond with the boron. So NH3 and BF3 have a coordinate covalent bond in between. Another type of bond, atomic bond that exists is a metallic bond. Each atomic nucleus is surrounded by the cloud of electrons. These electrons are free to move in the valence shells, and sometimes they also move from one layer to another. So that's why, because of the free movement of electrons, they can absorb energy. And also you can see metals are very have a shiny surface. It is because of the reason, and that because of the existence of the valence free electrons, because they can absorb energy and then they can move from place to place, emitting those absorbed energy in the form of photons. So each atomic nucleus in a metallic attract valence electrons of surrounding atom, which makes a metallic bond. Therefore, valence electrons are not bound to single atom and move freely in between atoms. However, net positive charge in the matter remains equal to the net negative charge. Metals are very good thermal and electrical conductors because of the movement of free electronic clouds. Then we can see, because of the covalent bond is directional. So when there is a covalent bond, you can see there will be a sharing of electrons, and before electrons will be making a covalent bond, they will arrange themselves in a specific direction and pattern as well. For example, in case of CH4, you can see central carbon atoms surrounded by the hydrogen atoms at a particular angle. So this is the example of methane. Similarly, we have example of the H2O, NH3, F2, and C2H6 as well. Under these special circumstances, S and p orbitals combine to form the hybrid sp-n orbital, where n is the number of the p orbitals involved. For example, here you can see CH4 and CCl4 and diamond have sp3 orbitals. How? You people know there is 1 part contribution of s orbital and 3 parts contribution of p orbital in case of diamond, methane and CCl4. So 1 orbital from s and 3 from p. So it will be making basically total number of 4 bonds. So here you can see this is 1 bond, this is second bond, this is third, this is fourth. Similarly 1, 2, 3 and 4. So total number of 4 bonds exist. So you can see the tetrahedral structure here, and interatomic angle is 109.5 degrees C. Atoms equally spaced around the central carbon atom. 109.5 degree is a time average angle that varies rapidly as the result of the thermal vibrations as well. So in case of sp-n orbital, we will see, for example, in case of H2O, you can see interatomic angle is 104.5 degree. In case of water, you can see, and in case of NH3, this angle is 107 degree. So angle of 109.5 degree is distorted when carbon is not bonded with the identical atoms as in CH3Cl. Greater distortions when electrons occur as lone pair as in evident NH3 and H2O. Similarly, we can see here we have a sigma bonds and pi bonds. In case of a sigma bond, we can see here that sigma bond will be formed with the sharing of electrons in between carbon-carbon atoms, and it will be horizontal, while vertical bonds or vertical sharing will be pi bond. Okay, so sigma bond is basically formed because of the axial overlapping, for example in carbon-carbon atom. So it is your axial overlapping, that is sigma bond. And in case of pi bond, you can see lateral bond. So there is lateral overlapping. So sigma bond is normally stronger than pi bond. Sigma bond is a pi bond is formed only in the addition to the sigma bond. What does this mean? First of all, sigma bond will be formed, and if still electrons sharing is available, then it will prefer to go for the pi sharing of electrons. But first preference will be for the sigma bond, or axial sharing will be the preference. Now we can see the secondary bonds that are basically the van der Waals forces. They are very weak forces that exist in between molecules. For example, in water atoms, H2O, you can see in between water molecule we have hydrogen bonds. Hydrogen bonds are strong. Okay, hydrogen bonds are strong than the van der Waals forces. So hydrogen bonds are stronger than van der Waals forces. But normally overall they are considered weak bonds. They consider a dipole, and because of the creation of a dipole, for example, one end will be positively charged, other will be negative charge, and it will create a dipole. So electrons will oscillate, and there will be the sharing of the bonds, and it will result in the formation of the hydrogen bonding. So bond length will depend upon the attraction force in between atoms, we can see that higher is the bond length, higher will be the bond energy, and higher will be the melting point, higher will be the boiling point, higher will be the strength of material. But in response, what will be inverse? A thermal expansion or thermal contraction will be in the reverse to the higher length of the bond. If bond length is small, melting point, boiling point, physical mechanical properties will be weak, but on the other hand the thermal expansion or contraction properties will be strong. So like atoms will create a repulsion force, for example electrons, and similarly unlike atoms will create, this is negative, this is positive, so it will create attraction force. And this is very important concept, please pay your attention. This is basically a bonding curve that exists within the molecules. For example, if I am going to create the energy curve for H2, I will see this is our x axis, this is our y axis. On x axis I will create the internuclear distance. For example, if these are two hydrogen atoms, then what is the internuclear distance? What will happen? What kind of energy will be there when these atoms are at very high spacing? And what, for example, you can see this type of energy will be basically because atoms are located far away, so you can see that it will be the repulsion force, it will be creating a repulsion force. And if atoms are very close to each other, it will have a very high attraction forces. So try to locate it on the graph. So this is your interatomic distance and this is your bond energy, okay, and this is your mean line, and you will see that first when atoms are located too away, for example one hydrogen atom is here, one atom is here, when I will bring them closer, then what will happen? Imagine, force of attraction will increase. What will happen? Force of attraction will increase. So I am denoting here the force of attraction with red curve. And now you will see that this force of attraction will be higher at the minimum distance. For example, the closest distance I can bring together two atoms. Now atoms are too closer, and in this case we have reached this point. Now after this point what will happen? Now because atoms are too much closer to each other, then because of the electronic cloud, now repulsion force will be there, and it will try to originate and it will increase the repulsion force. So this is your force of repulsion. Basically it will increase in very small amount of time. You can say that force of attraction increases for very large intermolecular distance, force of attraction, but force of repulsion increase abruptly. You can see here there is a sharp rise of peak when the atoms are too much close to each other, and because of this it will generate a repulsive forces. While this kind of red line you can see it is for the very long available distance, so I can distribute this force over the distance as well. So you can say that active area for the force of attraction is this one, okay, and active area for force of repulsion is this one. Now look into the steep of the curve. Steep of curve means depth of the curve. You have to check how much steep is the depth of the curve. What is the gradient? It is approaching perpendicular or not. If we have a higher steep, for example, let me compare here. For example, if I have two peaks for two atoms, for example, assume this is one bond curve and this is another bond curve. Okay, so these are two different steeper curves with green and red line. We can see for the red line, the distance from the mean line is basically the bond energy E naught. E naught is the bond energy. Okay, so basically E naught is required to disassociate the atoms pair. That means it is required to dissociate atoms to separate ions at R naught. So R naught is the point. This is the point where we will say that this is the R naught distance, and this is the point of dissociation where we can separate ions. Okay, and basically we are always interested to find the bond energy at this point R naught, because it is the point where we can separate ions. So it is equilibrium separation distance. R naught is equilibrium separation distance. And now we are going to compare this curve, and we can see that R naught for red line is higher and R naught for green line is smaller. For example, look here, this is smaller. Okay, so if R naught is higher, that means bond energy will be higher, E naught will be higher, and if E naught is higher, atom will have high melting point, high boiling point, high strength, electrical conductivity as well, but reverse will be that it will have a very low coefficient of thermal expansion or contraction. On the other hand, another R naught point, that is for the green curve, that is not much steeper. So because of the less steep curve, green line, you can say it will have low melting point, low boiling point, low strength of material, and higher will be the coefficient of expansion and contraction. Okay. So you can see basically this is your repulsion area and this is your attraction area, and we are representing energy axis, potential energy axis E, and this is the distance R naught where we can dissociate atomic pair, we can easily separate ions, and at this point amount of energy required to deassociate atom pair to separate ions at R naught, then amount of energy required here on the mean line R naught will be E naught. So this is your E naught, that is the bond energy. Okay. So you can see equilibrium separation distance have higher effect on the bond length. Higher is the equilibrium separation distance, R naught will be higher. What does this mean? Bond length will be higher. If bond length is higher, what will happen? Bond energy will also be higher. That means E naught will also be higher, and if E naught is higher, it will have high melting point, boiling point, strength, stiffness, and so on. And what will be low? Coefficient of expansion or contraction, thermal contraction and coefficient of thermal expansion, they will be lower. Okay. So basically ionic bond is non-directional bond while covalent bond is directional bond. So you can see here the elaboration. Deep and narrow through means more attraction energy between atoms and favoring solid state. Okay. Liquid and gas atoms have lesser deep curves, very important thing. So you can say solids will have very high value of R naught and liquid and gases will have low value of R naught. Deep and narrow through means low coefficient of thermal expansion and high melting point, I have already explained. Okay. Steeper slope is for stiff materials. Also, if slope is stiff and gradient is very high, then it will also make for the solids and stiffer materials. And if the steep is the shallower means less gradient angle, and we will get the flexible materials. So E naught varies from material to material and with increasing tendency from gas to liquid and then to solids. So what are the list of common properties we have studied? Atomic weight, atomic radius, coordination number, density, melting and boiling temperatures. They also depend upon the attraction repulsion forces and curve through. So basically this is the dependence, which property depend upon which parameter. Mechanical property, if we will look into mechanical properties, for example this is first property, density, and depends upon atomic weight, radius and coordination number. When we will look for the second mechanical property, that is melting and boiling point, it will depend upon attraction and repulsion of the curve through. And this is third property, hardness, it will also depend upon attraction force of the atomic level. And another fourth mechanical property is elasticity, it also depends upon the slope of the curve. So this is important of the energy curve, you can see. Similarly, thermal expansion is the inversely related inverse relation, and thermal conductivity depends upon the valence electrons and atomic vibration. Higher will be valence electrons, higher will be the vibration of materials, higher will be kinetic energy, higher will be the thermal conductivity. Similarly, we have electrical properties, higher will be the valence electrons, higher will be the electrical property. And similarly, we have magnetic property, we can say that higher is the rotation of atoms, higher is the spinning of electrons, higher is the magnetic property, magnetic quantum number will be higher, and you can say in these domains magnetic properties will be higher. Similarly, for optical properties, wavelength absorption and emission again depends upon the arrangement of atoms. So basically we have intrinsic and extrinsic properties. Intrinsic properties are internal structure properties, for example hardness, melting point, electrical conductivity, ductility. They are all because of the chemical composition. So what will be its hardness, melting point, boiling point, electrical conductivity, ductility. These are intrinsic properties. What are extrinsic properties? They are because of the quantity of material. Example, weight, area, height, thickness, volume. So extrinsic properties basically depends upon the volume, weight, area, etc. Okay. So in conclusion, we can say till now we have studied different atomic models that are available for the arrangement of the electrons, protons, neutrons, and different chemical bonds that are formed in between atoms. In these chemical bonds we have studied ionic bond, that was because of the highly electronegative atoms. Similarly, we have covalent bond, that is because of the less electronegative element, and we will have the sharing of electrons. Then coordinate covalent bond, where we have a donation of the lone pair of electron, and then we have studied the metallic bond, where we have the valence free electrons moving around. And then we have gone through the weak bonds like hydrogen bond and the van der Waals forces. So polymers also have a zigzag arrangement. When you will look inside polymers, they have a zigzag arrangement of carbon atoms. This is zigzag arrangement, okay, of carbon atoms, and in between these layers you will see this is zigzag arrangement, this is another carbon atom, and in between these carbon atoms there will be another force of attraction, but it will be weak force of attraction, weak forces. These weak forces will generate, and these are basically because of the coordinate covalent bonds or hydrogen bond. So these dash line force of attraction will be weak, hydrogen bonds or coordinate covalent bonds, sorry, hydrogen bonds and van der Waals forces bond, and they will be weak, okay. While in between these carbon atoms we have carbon-carbon bonds resistance. In case of polymers, you people will see that in between atoms there is a carbon-carbon bond, but in between layers of atoms we have the existence of weak forces like van der Waals forces or hydrogen forces. So that's why polymers have a low melting point because of the weak forces of attraction. So your covalent bond is directional bond, and in addition we have studied the energy curves for the steeper and shallower behavior materials having the deeper curve basically will have a higher bond length and higher bond energy and higher melting, boiling and strength properties as well, while on the other hand less is the steeper curve, that means higher is the shallower curve, and gradient will be also low, and in this way material will be having low melting, boiling point, strength properties but high coefficient of thermal expansion or contraction. Okay, so this was our week number 2. I am sorry for this behavior of the tab. This is because of the some problem within my device, so please ignore these kind of I will inshallah in future lectures I will avoid this kind of problem. Thank you very much for your time.